Alright, what's going on everybody? In this video, we're going to be talking about exponential growth and decay. Now you've probably talked about this earlier in your algebra years, but now we're going to be adding some calculus to it. These problems are going to get a little more advanced, but it's nothing to worry about. So let's go over the specifics of how this video is going to go down. So to start off this video, I'm going to give you an introduction to exponential growth and decay. Now, this introduction is going to include like the different definitions, right? We're going to get in-depth look of what exponential growth and decay actually is with calculus. When I was learning this, I got confused with a lot of the definitions earlier on, and so I do want to spend quite a bit of time on this. After we talk about the introduction, right, we will get into population growth, right? This is the first example that we'll talk about, right? This is definitely something that you've had to deal with before. We'll talk about radioactive decay, right? This is half-lives and everything. We'll talk about Newton's law of cooling. This is probably something that you haven't encountered before. Throw your room temperature coffee mug outside and see what temperature it's going to be in 10 minutes, right? That's Newton's law of cooling. And then we deal with compound interest, which again is something you've probably heard of before, right? So that's all coming in this video. Now, before we get into this video, I quickly wanted to mention my full Calc 1 course, which I have linked in the description down below. In this course, I have plenty more practice problems that you and I can go through together. And it's not just, a PDF worksheet and an answer key, right? Yeah, I have that. But if you're still, struggling with those problems, you've looked, you don't really get it, I have a full video where I go through all those practice problems, right? And so I'm not going to leave you in the dust for that. And so if you're interested in that, check out the link in the description down below. Now let's get into the video. We're going to start off with that introduction, right? And so a lot of natural phenomena, right? A lot of stuff in the real world exhibits exponential growth and decay, okay? And I actually just listed off some in that intro there, right? But what does exponential growth and decay even mean? Like mathematically, what does it mean, right? Well, the actual definition of it, and this is probably going to confuse you the first time I read it, but we'll talk about this stuff. Exponential growth and decay is where a quantity will grow or decay at a rate proportional to its size. Okay? So that might seem really weird, right? I mean, you might have been like, okay, yeah, a quantity grows and decays, right? That makes sense. But then when we talk about at a rate proportional to its size, what does that actually mean, right? And so to start off dissecting that, let's talk about proportionality. Let's talk about what that means. We'll just do a quick review. Okay, if I say that x is proportional to y, that relates these two, right? They're related. That means that if I increase x by 2, let's say I would increase y by 10, and that would always happen. So if I increase x by another 2 and I get 4, I would have to increase y by another 10, right? And so they're related. They have the same ratio, right? So how you can actually write this with an equation, right, is that, well, look at, this ratio between 10 and 2, right, and 20 and 4, right, 10 divided by 2, 20 divided by 4, right, all of this is equal to the same number, and that would still continue on if you just kept going with this, right? And so we could write that y divided by x is going to equal some constant. In this case, it was 5, but more generally, right, to deal with more examples than just this, we could just call it some variable, which is a constant, right, because it's not going to change for different values of y and x, but we'll just call it k. Okay, and if you actually multiply by x on both sides here, you get the equation of a line. And that's exactly what happens when you deal with proportionality of two variables, right? You get a line. Okay, and that line has a slope of k. So, anywho, that's proportionality. Now, what are we actually saying is proportional in this example? Well, we are saying that the rate of our growth or decay, right, which we could say, let's say we're dealing with a population, because that's the example that I pulled up right here. So, the rate at which something is going to grow or decay, right, is the rate at which the population changes, right? That's the same thing, okay? And we can call that dp dt. Or since I'm not really going to deal with any calculus yet, right, we're going to call that delta p over delta t, okay? And that is going to be increasing at a rate proportional to its size. Okay? So its size is just itself, right? Like the size of the population is measured by p, right? If p is 2,000, that means the size of your population is 2,000, right? So these things are proportional. So that means if you want to have an equation here, you could write this as, delta p delta t is equal to some constant k times p. Okay? And so for this example here, a population quadrupling in size, well, really, let's just think about what value of k would make that equation true. Let's think about this. Let's actually put this into practice, because still it might seem like a way too much notation for you to handle. So if we're talking about this thing happening every year, that means delta t would be 1 year, right? So we'll just say delta p equals kp, right? We're just going to look at how this population changes over 1 year, and we know it quadruples. So if p is 2,000, right? 2,000 would be multiplied by k here. What would our change in p be over a year? Well, if p is 2,000 to start the year, it's going to be 8,000 to end the year, and so it will have changed by 6,000. And so k here would be 3. We'll do another example. Let's say the population started out with 10,000, right? Multiply that by k. We end up with a population of 40,000 after a year, and so we've changed by 30,000. Again, k is equal to 3, right? And so this k right here, what we call this is it's our relative growth. We call it our relative growth rate. All right, and it's just showing us, how much we are growing relative to where we started, right? So we're saying, okay, we'll multiply this thing by 3, and you get how much you've changed over an entire year. Okay, and so another example would be 2% per year. Like that's our rate of increase. Okay, and so that's what k is. It's the relative growth rate. Now I do want to note that the example that I just gave you here, this it's not really like real life, okay? It's not very real life like, because the way I've just made this problem seem, it's that repopulation occurs by every year on December 31st, you get, a whole bus of people that comes in and it quadruples your population size. That's not how reproduction works, if you guys haven't, realized yet, right? You have reproduction always happening. The population size is always increasing. Like cell division, right? You always have cells that are dividing. And so that is where exponential growth really, starts to take shape in the real world. And so we need to, to talk about all the different population changing every single second, every single interval of time. We need derivatives. We need infinitesimal amounts of time to look at, these small changes in population. Okay, so that's why we're going to shift this equation to derivative form now. Instead of using deltas like we did up here, we're using d's. We're saying dp dt is going to equal k times p. And that is this equation in derivative form. That is the law of natural growth and decay. Okay, and so this equation is not only called, it's the law of natural growth and decay, cool, but more generally, it's a differential equation. And this might be one of the first times, or the first, that you're seeing a differential equation. A differential equation has a derivative in it, right? It has derivatives, it has, the function that it's taking a derivative of, right? It's all meshed into the same equation. And basically, this equation just kind of shows you how your population will change with time, right? It gives you that change when you input any population. So let's say I'm at 2,000. It's saying, okay, well, here's how that slope is changing at that point, right? Or how that population is changing at that time. Okay, and so that's the idea with this equation. We're not really going to use it though, and we'll actually be solving this for p, because it's cool. This equation, if you write this with y's, it's saying like, oh, dy dx is equal to k times y. oh, that's great and all, but what's y as a function of x, right? Like, what's the actual solution to this? Okay, and we can actually extract that information, right? We can extract the information that we just talked about, that equation for p, that equation for y, right? We can find that by extracting from the law of natural growth and decay. We can reverse the derivative process that would have led to this kind of equation in the first place, right? Because we have derivatives, so we would have had to take them at some point, right? So we can reverse that derivative process by taking an integral. Okay, now when I learned this in calculus, I was taking AP Calc AB at the time. I had no idea what an integral was, and so when I would look up YouTube videos, I would see, and yeah, I watched YouTube videos too, which is weird because now I'm that person that's in the YouTube video. But I would see those integrals and I'd be like, what the heck is this? And so everybody would try to explain it that way, and I'd be like, I don't know what this is yet. So I'm not going to explain this with integrals. I'm not going to show you how to solve it with integrals. I'm just going to show you kind of like a little thought experiment that we can do to find this out. Okay, what I'm saying is, if dp dt is k times p, what is one possible answer for what p could be? And actually, there's really only one thing p could be here, and that's an exponential. Why? Because the derivative of p, like if we just kind of forget about the constant here for a second, right? For p to be equal to its derivative, right? It would need to be an exponential, right? Because the derivative of an exponential is itself, right? And so here, though, we have a constant. And so what that means is that maybe we'll start off with e to the kx, right? And when we take a derivative of that, we get ke to the kx, right? And so, we need to account for that by including a k out here. But anyways, so what we're actually going to do, and the real solution to this, is actually not just e to the kx, but it's ce to the kx. Why would we have a giant constant out here? That's what c is in this case. Well, if we actually plug in to this equation, let's see what happens. We have a d dt, and p now we know is ce to the kx, and actually it's not kx, it's going to be kt here, because I'm talking about time. But it's going to be ce to the kt equal to k times, well, ce to the kt. Okay? And, well, the time derivative of ce to the kt, that right there is going to be ce to the kt times the derivative of the inside here, which is k. And that's equal to the other side. Okay, and so you see here that, constants get ignored in the derivative process. So there technically could be a constant out here, and, we would still get the exact same thing on both sides, and we would still get the same answer because the constant gets ignored. So that's why we can have it out there. Again, you don't really need to remember all of this, right? You just need to have a vague idea of what's going on to be able to do the problems. But anyways, yeah. So anyways, p ends up equaling ce to the kt, and what you'll realize is that c is the initial population. That's why we actually want that constant there, right? That constant is going to tell us the initial population. That's cool. So our equation is that our population after some time, t, is equal to the initial population times this exponential. Okay? So now let's get into actually doing some problems with exponential growth and decay, and since we're on the topic, we'll start with population growth. So in actually getting to our population growth practice problem here, we are going to start with this example. We have that in 1950, the world population was 2.56 billion. In 1960, this population had increased to 3.04 billion. Assuming that the growth rate is proportional to the population size, what is the value of the following? And A says the relative growth rate, B is asking for the population in 1993, and C is asking for the population in 2020. Now, we are given this little bit of information down here, which I think would cause the most confusion, and that says, assuming that the growth rate is proportional to the population size, right? That's exactly what we talked about in the introduction, right? That just means we're dealing with exponential growth or exponential decay, okay? And here, since it says growth rate, we're dealing with exponential growth, okay? So, how do we find the relative growth rate? And when we say relative growth rate, right, we mean K. Okay, and that's also something we talked about in the introduction, right? So the relative growth rate is always found by using the information, the initial information that you were given in the problem, right? You're generally given 2 times, right? Or like a starting time and ending time, right? And you're given 2 values, your initial value and your final value. Okay, and really it all comes down to plugging into the equation. You plug into P equals P naught times E, right, I say P naught, I mean you can say P initial, it doesn't really matter. Anywho, so that is going to be the start of part A here. Right, you're plugging into this P equals P naught times E to the KT equation. And, well, what do you plug in? Well, let's think. What is our P, what's our P naught, and what's our T, right? We're going to need all of those because we want to find K, right? We need every other variable to be eliminated. So, well, P is our final population, and that is 3.04 billion. So we can just call that 3.04 and realize that, you know, this is units, well, not, you can think of it as units, right, of billions, okay? And then we have 2.56 billion. That's our initial population. And then we have e to the k times how much time has elapsed. That's what t is asking. How much time from when you were at your initial population? And when we were at our initial population, it was 1950. And if you think of 1950 as t equals 0, then 1960 would be t equals 10. And so that's why we put a 10 here, right? It's a lot easier than, you know, I mean, it's a lot easier to think about it that way than to think about plugging in like 1960s, 1950s, all that stuff, right? That'd be really gross. So, now that we have this, we just solve for k, okay? And how we're going to do that, we're going to isolate this exponential, and then we can take natural logs of both sides. But how do we isolate that exponential? We need to divide by 2.56 on both sides. In doing that, we are going to get 1.1875 is equal to e to the 10k, and that just glitched out a little bit. Okay, now that we have this, we take the natural log of both sides. Okay, and we don't really need, I mean, you can put this in your calculator already if you want, but I think it'd be a little bit of a waste of time because you're going to do that, you're going to be plugging in some really gross number later anyway, but that's besides the point. You'll see that later in this problem. So we have the natural log of e to the 10k. We can rewrite that as, well, a 10k times the natural log of e, right? We can move that exponent out front of the natural log, right? And so maybe it'd be easier to think about it as 10k times the natural log of e, right? Like that, rather than 10k natural log of e. Same thing though. And you know, the natural log of e, that's just 1. So we're left with a 10k on this side. To get k by itself, right, to finish solving for k, we just divide by 10 on each side, right? And what we're going to get is that k, when we plug that into our calculator, and you can see why, right? It would be a waste of calculator time to plug in that natural log and then get another decimal and then have to type that decimal in again and divide it by 10, right? It would just be, I don't know, it would just be a waste of time. Anyways, so we get that k is equal to 0.017, right? And that is 1.7%. That right there is our growth rate. And so that is the answer to part A, which, so I'll circle that in red. Okay? So that's the answer to part A. It's just the growth rate is 1.7%, and it's going to be 1.7% per year. Okay? That's essentially what K means. So then we are asked the population in 1993. Now the population in 1993, right? that means that, like, which variable are we trying to find here? Well, it means we're trying to find p, right? Because p is going to be the final population after, well, how many years? Well, 1993 minus the initial time of 1950, yeah, that's going to be 43 years, right? So t is going to equal 43 here. We know our initial population is 2.56 billion. We know our k is 1.7%, or we could, it's going to be a little easier to plug that in decimal form. All right, and so now we just plug all that in, and that's how we find p. So we say 2.56 e to the 0.017 times 43. And that will give us an answer of 5.36 when you plug that into your calculator. 5.36 billion. Okay? And that is the answer to part B. Now, it's the same exact thing, right? They might ask you a couple different times, right? And like they could ask you the population in 2030, right? And then they would probably say, oh, well, predict the population in 2030 instead, right? They'll say something like that, right? And well, as of right now, as I'm recording this video, we're in 2020. But let's say that I was recording this video last year and it was in 2019. Well, then it would have said predict the population in 2020. Okay, that really doesn't mean anything. Let's keep going here. All we're going to do now is, instead of plugging in t equals 43, we're going to plug in how many years are between 2020 and 1950, right? And that would be 70, right? So we do the exact same thing again. We write down all our information that we need to plug in here. And we just go ahead and go for it. So we do p equals 2.56 e to the 0.017, right? Times our time of 70 years. And that gives us a grand total of 8.52 billion. All right. And so it's kind of interesting. Well, it might be for you, but if we just, if we were living in 1960, right, we had the population data over the last 10 years, and we compared the population in 1950 to the population in 1960, and we assumed exponential growth, we would have predicted the population in 2020, which, by the way, this population right here isn't that far off. You could consider it an estimation, right, because we're taking it from the 1960 data. And so there's an example of a real world use for this, right? We're using it to predict trends in the future. So now we're going to move on to talk about radioactive decay. Now, radioactive decay is pretty much the exact same thing as population growth, right? It's going to differ for a few reasons, right? But it's more or less the same idea. If you understand population growth, I promise the radioactive decay is not much more difficult, if at all. Okay, there is one little key difference in the problem, but like in doing problems, but there are, just kind of more generally, if we're not just talking about like the problems here and more talking about the conceptual stuff, there are two key differences there. Firstly, instead of growth, right, before we were talking about population growth, now we're talking about radioactive decay, right? So instead of growth, we have decay. And what decay means is that k is less than 0, okay? And that should actually make sense to you. Why would k be less than 0? Well, if you actually look at this equation down here, right, which we'll get to in a second, but we're going to have that mass is equal to the initial mass times this exponential, right? It looks like the exact same thing as the population equation, but think what happens if you have if k is a negative number. If k is a negative number, then this thing is going to be kind of like flipped, right? So instead of having e to the kt, it's going to look like 1 over e to the kt, right? I mean, assuming that you're using like the absolute value of k there, because you would have to, switch the sign going from here to here, right? But that's the whole point of a negative exponent, right? It would flip it down to the denominator, right? And now you have this quantity here, right? That as time increases, this entire thing is getting, well, I mean, the denominator is getting bigger and bigger and bigger, so this entire thing would get smaller and smaller and smaller, right? So now you have a smaller and smaller and smaller number being multiplied by your initial mass, right? And so your initial mass keeps decreasing and decreasing and decreasing, right? And, well, that gives you, your final mass. So that's the idea with decay, okay? Now, instead of population, we have a mass here, right? We're talking about a mass that is decreasing, okay? And so what we do is, instead of using p like we did before, right? We said dp dt is equal to k times p. Now we're using m's for mass, right? And then this is how the actual solution to this differential equation is written. And this is the equation that we're really going to be using here, okay? But it's good to know where it comes from. So in radioactive decay, we like to talk about the half-life of a substance, right? We talk a lot about half-lives, and so we need to get comfortable with, what's new with that addition. What changes when, now that we have half-lives, where is, with population growth, we didn't talk about that as much. We didn't talk about that at all. So the half-life is the amount of time required for half of the quantity to decay. So after one half-life, you have half of the mass that you originally did, right? So if we know that, let's actually apply this. And this is something you're going to see in pretty much any radioactive decay problem. If we look at the m of t equation, right? That means this equation, right? M of t is this thing, right? It's m after some time t. Well, looking at that equation, let's say that your half-life time has occurred. What is your new mass going to be, right? And so that's it seems like a really vague question, right? Like, we're not given any actual information here, it seems like, other than that we know that a t1 half has occurred, right? So we're not plugging in any numbers here necessarily, but what we need to realize is that if we start out with mass m naught, right, that's our initial mass, and we go for a half-life, well, how much mass is going to be left? You would say m naught over 2, right? Half of it. And m naught over 2 would be, again, your mass after one half-life has elapsed, okay? So that's the idea. So in solving for k, which is, again, this guy right here, we have to do that in pretty much every single problem, right? Unless we're given it like in compound interest, you're generally given k. But I mean, again, when we're trying to find k, we're going to be plugging in m naught over 2 for that m a lot of the time. Okay, and so I just want you to watch out for that. In this example that we're going to do right now, you're going to see that happen. So the example I have for you here is that the half-life of substance X is 1590 years. Given that we have obtained 100 milligrams of substance X, find the following. And we have a formula for the mass of our sample of substance X that remains after t years. Okay, and then B is asking for the mass of our sample after 1,000 years. C is asking when the mass will be reduced to 30 milligrams. Okay? So we're, for part A, right? We'll start off with part A. We are asked, to find a formula for the mass of the sample of, in the samples of substance X, right? So we're finding a mass of this sample that remains after t years, right? So basically what we're going to get here is we have our m equals m naught e to the kt, right? And we just want a function where we know what m naught is and we know what k is, right? Because we want the only variable to be t. What we want to do is be able to plug in a t, right? So we have m as a function of t and have something like 200 e to the, let's say, 3t, right? To where we can just plug in a t and then get our mass at that time, okay? So how do we do that? Well, like always, we want to find k, right? That's really how we're going to start this problem. And so how do we do that? Well, let's actually write our equation again. M equals m naught e to the kt. Okay, what do we know? We know that this half-life is 1,590 years. Okay, so that's something we can write down. We also know that we start out with 100 milligrams. That's m naught. Now, looking at this information here, right, we're given a time, we're given a initial mass, right? And if we plug those in, right, we have 100 milligrams, we have, which we don't even need to include the units really. This is math, not physics. We have 100 times e to the k times, and we're given a half-life, we could plug that in, right? We'd have k times 1590, right? But how are we going to solve for k if we don't know what m is? Well, this is where that trick comes in that we just talked about, right? After your half-life has occurred, you're left with a mass of half of your initial mass, right? So this m right here becomes, well, it becomes 100 over 2, right? Because that's your initial mass just divided by 2. Here's an even bigger thing. They don't even need to give you your initial mass. Let's say we didn't know what our initial mass was. What can we do to figure that out? Right now we don't know k, we don't know m naught. Well, we can divide each side by m naught, right? And now look what happens. They all cancel, and we're left with a 1/2 equals e to the 1590k. That's pretty crazy, right? We don't actually even need the initial mass. All we need is the half-life. And if we're given the half-life, we can find what k is. Okay? Because we know that after, one half-life, we know the relationship between these two things, right? This is going to be half of this. Okay? So let's keep going here. Let's start finding what k is. All we have to do for that is take a natural log on both sides. Okay? If we take a natural log there, we're going to get the natural log of 1/2 is equal to, we can pull that exponent out front, right, and get 1590 times k, right? And then we're left with a natural log of e, right? And natural log of e is just 1. So then to solve for k here, we divide by 1590 on each side. Okay? And when we do that, we get that k is equal to, and we don't even need to plug this into our calculator or anything, right? It might just be a little bit of a waste of time. Okay, we can just write k as natural log of 1/2 over 1590. Okay, I mean, it might be easier for you to look at a decimal, right? But I mean, it's up to you, I guess. So here's the deal. We can check to make sure, right? We said that k has to be less than 0. Is k less than 0 here? Well, yes, it is. How do I know? Because natural log of anything that is less than 1 is going to be negative, right? And of course, natural log of 0 or anything that is less than 0, like -1, -2, that doesn't exist. But if you have natural log of x, right, where x is in between 0 and 1, this thing is going to be negative. Okay, plug in any fraction that is less than 1 in here, and I promise you, you will get a negative number out. So that's a good sanity check, right? We know that this is negative. K has to be negative for it to be decay, right? So that's a great way to check yourself. Now, let's actually solve this problem, right? We want to find the mass after t years. So we're going to set up that m of t equation. Okay, we know that, again, the equation is m naught e to the k times t, but now we know both m naught and k, and we're not going to plug in for t here, right, because that's supposed to be the variable that we can plug in, right? We want to be able to plug in any t, not just the half-life. So m naught is going to be 100. Okay, right? That's the initial mass. And then we have E times a natural log of 1/2 over 1590 plugged in for K. And then we have a T. All right? And that right there is the answer to part A. All right? Awesome. So now let's move on to part B. Part B is going to be a lot quicker, I promise. The mass of our sample after 1,000 years is the next thing we're about to find, right? So really, all we have to do, now that we have an equation for our mass as a function of time, we can just plug in the amount of time into our equation. We can say that m of 1,000, right? We're writing 1,000 here because we're showing that we're plugging in 1,000 for t, right? This is going to equal 100 times e to the natural log of 1/2 over 1590 times 1,000. Now this right here, this is going to equal 65 milligrams. Okay? You just got to plug that into your calculator. Make sure that you're using parentheses correctly so this entire thing ends up in an exponent and you don't end up just, accidentally multiplying by the 1,000, not in the exponent like somewhere down here, right? Just make sure you're using parentheses correctly. If you didn't get 65 milligrams, that's probably why. So that's the answer to part B. Now let's talk about part C. Oops, let's get the white back. All right. So when will the mass be reduced to 30 milligrams? Well, that would give us, again, we're going to use our m of t equation. That would give us a m of t of 30, right? We're looking for when this mass ends up being 30, right? So when 30 is equal to 100 times e to the natural log of 1/2 over 1590 times t. Okay? That's all we're doing here is just solving for t here. Now, a lot of people, they'll see this, right? And they'll be like, oh my God, how do I solve for t at this point? I get that, right? I would get confused when I looked at these all the time, okay? But again, when you have like anything with e or an exponent, right? The key is to isolate that exponential. Isolate that thing with t in it, right? Isolate that thing with the variable that you're trying to solve for in it. We can do that by dividing by 100 on both sides, right? That's just the first step. We'll take this one step at a time, as you should with any problem. So 30 over 100 is going to be 3/10. Okay, we don't need to put that in our calculator really. I mean, we can leave it as a fraction for now. Okay, and then we're left with e to the natural log of 1/2 over 1590 times t. And then to solve for t, we need to get this exponent out of here, right? We can't have an exponent with our variable in it. And so what we do is we take that natural log on both sides, right? We take a natural log, we have this e here, right? That natural log is just going to get rid of that e, right? Because natural log of e is 1. And when we have a natural log of something to a power, we can move that power out front. So we get that natural log of 3 over 10 is equal to, well, just the natural log of 1/2 over 1590 times t. Okay? And now we just divide each side by natural log of 1/2 over 1590. Right? Divide each side by natural log of 1/2 over 1590. Awesome. Okay? And now we have what t is. T is going to be the natural log of 3 over 10. Right? See if you can follow my logic here. This would actually be multiplied by 1590 in the numerator, right? Because this 1590 would come up. This natural log of 1/2 would be the base, right? It would be the denominator of this guy, right? So we would get over the natural log of 1/2. Okay? And that right there, when you put that all in your calculator, which is not as hard to put in your calculator as this mess, right? When we put all this into our calculator, we are going to get 2,762 years. And that is our answer for part C. So just a quick review of, what we did with radioactive decay, right? We said that now we're dealing with decay. We're using the variable m. We have our equation that we're going to use for all these problems. Now, like usual, we start off by finding k, and I'll talk about that in the problem here, but, we saw that the big trick for radioactive decay was going to be, using that half-life to our advantage, right? We know that our mass after that half-life has elapsed is going to be 1/2 of our initial mass, which you can write as m naught over 2. Or if it helps you, you could write that as 1/2 m naught, right? So we did our problem. We started off by finding k, right? That's usually what we have to do in any problem. We start off by finding k, right? And that gave us our equation for m of t, right? We used the m of t equation to find what the mass would be after 1,000 years, right? And we also figured out the time it would take for us to get a final mass of 30, okay? And that just involved doing some algebra, okay? So that's it for radioactive decay. So now we're going to move on to Newton's law of cooling. And if you got through radioactive decay, you'll get through this one too, okay? There's really not much more added difficulty. Just instead of having to deal with half-lives and their effect, now you have to deal with a bunch of different variables and how to actually use them in the problem to get what you want, okay? So let's look at how this differs from what we've talked about thus far, that being population growth, and you have... What else? What did we just talk about? We talked about radioactive decay. All right, so here's the thing. We're still dealing with decay. If something's cooling, right, its temperature is decreasing, and its temperature is actually going to look like this as it decreases, right? It's going to get closer and closer to the what? It's going to get closer and closer to the surrounding temperature, right? And so we're still dealing with a decay here. Now, the second difference is that instead of dealing with mass, we're actually dealing with temperature, okay? Right? That's the difference in variables here. So instead of using an m, we're going to use a t. All right? And so here's our new equation. Try not to let this overwhelm you right off the bat. Okay, I promise I'll explain this. And I'll explain why this looks a little bit different than we've had before, right? Now, you would probably assume that this equation, right, the change in temperature over the change in time, would equal k times a variable, right? That would be consistent, or, k times t. That would be consistent with everything that we've done so far, right? Like the change in mass over the change in time, right, dm dt, would equal k times m. Right? And, that was the same thing with population growth. But here we have a minus ts on the end. Why? Well, think about it, right? If the temperature, wait, that's t. If the temperature of our object, right, let's say we throw a coffee cup outside, right? If the temperature of our object has matched the surrounding temperature, right? It's now the temperature of the snowbank that I threw it in, right? Then we shouldn't be getting any more change in the temperature, right? This thing should be 0 if the temperature of the coffee cup matches the temperature of the snowbank, right? They have to be in thermal equilibrium is how you would say that in the science way, all right? So, well, let's think about it. Let's say that, okay, well, now our temperature is the surrounding temperature. Well, then dt over dt would be k times ts is going to be the new temperature of the coffee cup, right? The surrounding temperature, the temperature of the snowbank surrounding the coffee cup. Okay, ts minus ts is going to be 0, right? And so we would get that dt over dt would equal 0. And that would make sense, right? Again, there shouldn't be any change in the temperature if it's already matching the surrounding temperature, okay? And so when you solve that differential equation, okay, I'll just give you the solution here. We're not going to go through how you get this, right? You get this equation. Okay, this is the equation that we're going to be using. All right? And I know it has a lot of variables in it, right? But I have them all written down here. The first thing that you'll see is the T of T notation, right? That means the temperature of an object after some time t. Okay, think about it as our final temperature. Okay, that's what it is. And so if you want to denote it as T sub F, do that, right? And I think that would be a good indicator of what that actually is supposed to be. Now your TS is your surrounding temperature, right? This is, again, like let's say I was trying to figure out what the final temperature of my coffee cup would be when I threw it in a snowbank. The T sub S is the temperature of that snowbank, right? That's what I mean there. Now we have the initial temperature, right? That would be the initial temperature of the coffee cup. And then you still have your K, right? That's your, we used to call that relative growth rate with population growth. Now that is called relative decay rate, right? Because we're dealing with decay instead of growth, okay? And then of course you have little t, which is time, all right? So if you understand all of that, when you're reading your problems, it's a good idea to start marking out that information. Okay, we'll do that here. This example says, suppose I have a box which contains my dignity. I can't believe I made this problem. All right, so the box is at room temperature, 72 degrees Fahrenheit, but I decide to make a few Tik Toks, and for that I need to temporarily throw my dignity box outside in the frigid 44 degree Fahrenheit weather. Basically my way of saying that I have no dignity because I make TikTok videos. Anyways, after half an hour, my box of dignity has cooled to 61 degrees Fahrenheit, okay? And to stop the cringiness of this problem, let's stop calling it my dignity box, and we'll just call it the box, all right? So after half an hour, my box has cooled to 61 degrees Fahrenheit. So before we even read the questions, right, the A and B part, let's actually just mark out the information that we know now. The box is our object here, and it is at room temperature, 72 degrees Fahrenheit initially, right? So we're going to say T naught is equal to 72 degrees Fahrenheit. Bam. Now, I'm throwing that box outside into 44 degree Fahrenheit weather. So that means the surrounding temperature, right, the temperature that is surrounding that box, which is now going to be outside, is going to be 44 degrees Fahrenheit. Okay, and after half an hour, my box cooled to 61 degrees Fahrenheit. Okay, so there's two bits of information that you can pull there, right? You can either write this as T after a half an hour, or if you want to write this as 30 minutes, you can too, right? All the math will still work out the same in the end. You could write this as T of 1/2 equals 61 degrees Fahrenheit. Or if it helps you a little more just to really see everything going on here, you could say T of T equals 61 degrees Fahrenheit, and write that T here is going to be half an hour. Okay? So now we're saying what is going to be the temperature of the box after it's been out there another half an hour, right? So after it's been out there a total of T equals 1 hours. So here's the thing. We have all this information here, right? And let's look at, let's just look at our equation, right? And see what values we don't have. And I guarantee you it's going to be the K, right? It's going to be like the only thing we don't have is K. Watch this. T of T, we have that. T of S, we have that, right? Do we have a T naught? Of course we do. Surrounding temperature, we already said that. We have a time, we don't have a K. And so that's what we're going to have to find, okay? And so the K is going to allow us to talk about other cases where it's not just been a half an hour, but it's been a full hour, okay? So we're going to do that now. Let's start just solving for K. So T of T is going to be 61 degrees Fahrenheit, okay? And just to make this a little easier to read, we'll just say 61. T sub S is going to be 44. T naught is going to be 72. TS, as we just said, is 44. Then we have E to the K times 1/2. All right, now we're solving for K. Again, we're just going to have to get this exponential by itself, and so that's going to require a little more work than it did in the radioactive decay section. But there really aren't any tricks with this, right? We're subtracting 44 on each side. Okay, then we would get, this will be 11, this will be 7. Lower that to a 1, this will be not, what am I doing? This will be why did I do that? This is 5. Jeez. I can't believe I just failed at that. All right. I'm not even going to edit that out because I do want you guys to see that I'm human and I make mistakes. But anyway, 72 minus 44 is going to be 28. Okay? And so we get e to the k times 1/2. And then we're going to get that exponential by itself. So we're going to divide by 28 on both sides. And we get 17 over 28 equals e to the k times 1/2. And I'm giving a little bit of room here because now we're going to take a natural log on both sides. When we do that, right, the exponent comes out front. The natural log of e is what's left, and that's just 1. So we get that natural log of 17 over 28 is going to equal 1/2 times k. All right, and so now we just divide by 1/2 on both sides, and we get that k is equal to 2 times the natural log of 17 over 28. Awesome. So now that we have k, right, we can actually do the real problem, right? And so the real problem is finding the temperature of the box after another half an hour. So we're trying to find the temperature of the box, right? We're trying to find T of t. Well, actually T of 1, right? We're trying to find the temperature after 1 hour, right? And so what we're going to do, let's write out our equation, right? We have, let's remember what it actually is. So I'll duplicate it, I'll bring it down. Right? We have this guy, boop, boop, there. T of 1, right? So we have our surrounding temperature, we know, is 44 degrees Fahrenheit. Plus our initial temperature was 72. Our surrounding temperature, again, is 44. And then we have e to the 2 times natural log of 17 over 28. Right? And so if you want to simplify this a little bit before you plug it in your calculator, you can. This is going to be 44 plus 28 times e to the 2 times natural log of 17 over 28. And actually, if you want to simplify this even further, you could have chose to realize that, well, you could have realized that this can actually be rewritten as e times the natural log of 17 over 28. And this thing being squared, right? This part right here being squared. So I guess I can put that inside of I would need double parentheses here. So I would do this, right? This thing's being squared, right? That's what the 2 outside of the natural log can do. And we know the e in a natural log and the power is going to cancel out. And so this would actually just become 17 over 28, all squared, right? That's what this entire thing would become. Okay, and so, yeah, we could write it like that if you want, and so you could write this as 17 over 28 squared. Okay, if that way didn't make sense to you, it's fine, just plug that in and you'll be fine. Okay, but anyways, when you plug this in, you're going to get your temperature after 1 hour is going to be 54.3 degrees Fahrenheit. And that's your answer to part A. Let's move on to part B. Did I ever write that this was part A? Of course I didn't. Boop, boop. There we go. So part B says, how long after I've thrown the box outside will it reach 50 degrees Fahrenheit? Right? This problem is the exact same thing as when we did radioactive decay, and it asked in part C, when will our mass be reduced to 30 milligrams? Right? It's going to involve us plugging in for our m of t, or in this case, we're going to be plugging in for our t of t. Right? We know that this problem is asking for the temperature of 50 degrees. It's asking for the time it takes to get to the temperature of 50 degrees Fahrenheit. So let's plug that in. We get that 50 is going to equal, remember our equation here, right? It's our surrounding temperature, which is 44, plus our initial temperature, 72, minus our surrounding temperature, which is 44. And if you don't want to keep writing that, you don't have to, right? You could just write 28. Okay. You can write an E to the, we know that K is going to be 2 times the natural log of 17 over 28, right? And T here is going to be left. And if you're wondering, what happened to my T up here? Well, T was 1, so it was like multiplying this thing by 1. Okay, so hopefully I wasn't a little too confusing there. I did leave that part out. Okay, so anyways, here though, we don't know what T is. Okay, we're trying to find that because that's the only variable in this problem. So we can start plugging into our calculator, or you could solve it first and then plug in later, right? Because you'll have to solve it in your calculator or just solve it on paper and then plug in your calculator. Really up to you. So you get 6 is equal to 28 times this monstrosity, right? You get 6 equal to 28 times e to the 2t natural log of 17 over 28. So now we can divide by 28 on both sides. And when we simplify this fraction, we're going to get 3 over 14 is equal to e to the 2t natural log of 17 over 28. Taking a natural log of both sides to get rid of that exponential, we are going to get that natural log of 3 over 14 is equal to 2t times the natural log of 17 over 28. And then just solving for t here, we can divide on each side by 2 times the natural log of 17 over 28. Okay, and when we do that, we are going to get that t is equal to the natural log of 3 over 14 all over 2 times the natural log of 17 over 28. All right, and this right here is going to give you 1.54 hours. If you want to write that as minutes, it would have been 92.6. Okay, and so, again, if you wanted to, at the start of this problem, if you wanted to write your t in terms of, instead of in terms of hours, if you wanted to write that as 30 minutes, you could absolutely do that, right? And then you would get your answer, your final answer would have been that t is equal to 92.6 minutes. So that's going to do it for Newton's law of cooling. And now we can move on to continuously compounded interest, which is our last topic for this video. Okay? Now, listen, I'm going to be real with you. I had to review a lot for this topic because continuously compounded interest, I remembered, was actually something that would trip me up when I was in algebra 2, right, or around, that level in high school. I would get to, compound interest, and there'd be all these different types of interest, and then there was continuously compounded interest, and I didn't really understand what that means. So if you feel the same way that I did, let me explain to you basically everything about continuously compounded interest. It's actually pretty interesting, and I mean, for me, it might not be interesting for you, but I'll try to make it interesting for you. It's just, watch. So what the heck does it mean for something to be compounded continuously? Okay, like what the heck does that mean, right? You're used to saying something, oh well, you're gonna have something compounded once per year. You're going to, every year you make 6% interest on something, right? This example right here says, let's say that I'm Elon Musk, okay, and I have invested $1 million into a new tech stock. This tech stock is going to give me 6% interest. Now, when we talk about interest, okay, we talk about having 6% interest. This does not mean, here's a very common misconception, this is not going to mean that I'm going to make 6% on the year. That doesn't mean that I'm going to end up with $1,060,000, right? That's not what I'm going to have at year's end, okay? The reason for that is because the amount of money that I'm going to make from day to day is going to change. Why? Because the amount of money that I have invested is always increasing. So when would you get 6% on the year? Well, you'd get 6% on the year if you didn't reinvest any of the money that you were making. That's the idea with compound interest, though. Let's say that I start making money off of my investment. After every penny I make, I take that and keep it, right? So I still have $1 million invested at all times. Anything that I make from that, I'm going to take and keep. Then I would make 6% on the year. But here's the thing. Every day, let's say everything I've made, I just keep that in my investment and I reinvest it essentially. Well, then I have more and more invested after each day. And so I'm getting more and more interest off of that, right? And so that 6% is going to mean a lot more to me. So let's talk about that. Okay. Now you might think, okay, well, you're getting more and more and more every day. So that means you're going to get infinity dollars, right? You're going to basically win Monopoly, right? No. Let's use the compound interest formula, and I'm going to show you that just because we are, we're compounding an infinite amount of times, right? We're always reinvesting. That does not lead to infinite money. Now, you might remember this monstrosity from your algebra days, right? This equation right here. It looks pretty intimidating. Okay? You have that your money after time t, that's what A of t stands for, equals your initial amount of money that you have invested, times 1 plus r, which is going to be your interest rate. Okay? That's your interest rate. I'll write rate down here to make that a little more clear. Over the amount of compounds you have per year, which I think we should clarify what compounds are in just a second here. But then it's multiplied by n, which is again your number of compounds per year, times time, and time would be in years, right? If you're talking about the number of compounds per year. So here's the thing. Compounding, right, means that, let's say that I wasn't reinvesting any of the money that I was making from my investment, right? And I just sat and saw what amount of money am I going to make after a year, right? Well, let's see. A of t would equal my initial amount, right? Let's just call that A naught for now. I know it was 1 million, but let's just call it A naught, right? And then I'm going to multiply it by 1.06 to get the new amount of money that I have in total, okay? But let's say that I was getting 6% interest twice a year. Well, that means I would be compounding twice per year, and I'd multiply by 2 1.06s. Okay? I'm not saying that I'd make 6% interest on the year, okay, or else I would have to change these numbers because you have an over n here, right? But let's say I was making 6% interest 4 times a year. Well, then I would need to multiply, I would need to compound 4 times per year. That is quarterly compounding. So that's the idea. That's what compounds mean. Okay? It's the amount of times that you're making that interest per year. We're going to show, what we're about to show is that if we compound an infinite number of times, okay, we are not going to make an infinite number of money, or an infinite amount of money. Here it is. After 1 year of 6% interest, a $1 million investment will become worth the following, right? If we only compound once per year, right? That means that once per year, right, we're taking all the money that we make from that investment, okay? And we do that, and we will have $1,060,000 after 1 year. If we do semi-annual compounding, meaning that we're going to take all that money from our investment, right? We're just going to take it all. We're going to play it safe, right? We're going to take all that additional interest, and then after, let's say it's been half a year, we're going to put all that money back in now. Okay? Who knows why somebody would do that, but that's what semi-annual compounding is like. You can think of it like that, right? And then you wait for another half a year, collecting all the new interest from your larger amount of money that you have invested now. And now you see at the end of your full year, how much do you have in total? Okay, I know that's a little complicated, but just try to stay with me here. What you would now have, since for half the year, you had a larger amount of money invested than just that million, you would have this, right? And so this is 900 more than what we would have had we not done semi-annual compounding. Now, if we did quarterly compounding, right? So the same idea, but now we're just doing that more times per year. Well, then we would have just a little bit more. This is not going to increase as much. Notice that here we increased by 900. Here we're only increasing by like 400, right? 464. And then let's bump it to monthly compounding. You see that we increase again, but by even less. And then daily compounding, right? We're doing this weird cycle every day. Well, now we're increasing. This time we're only increasing by like less than 200, right? This looks like 150 or something like that, right? And so if we're increasing less and less and less, right, you would expect that at some point we would stop increasing by like any significant amount, right? We would just, we wouldn't go all the way to infinity. It's going to just kind of like asymptote. And that's exactly what happens here. Think about it. What's going to happen here? When we have an actual investment, which is continuous compounding, right? And I'll talk about what that is in a second, right? The limit as n approaches infinity, right? So we're saying that the amount of compounds that we're making goes to infinity. This is going to equal a naught times e to the RT. That's what this thing becomes. That's what this interest equation becomes if you have continuous compounding. Again, continuous compounding means that instead of like being weird and just, kind of like taking everything that you make, right, for a full year, right, and not letting any of that still like keep piling up in your invested money, right? Basically, what this is saying is that anything that you earn from that investment, you're just going to reinvest that. That's all going to, pile on to your investment. And now you'll make even more money because you have even more money invested. Okay? That's what continuous compounding means, is that it means that, all the money that you're making is going to help you make more money. So when you have continuous compounding, you get this equation. Okay? And actually, as a side note here, this might interest like 5% of you, 10% of you, I don't know. It's kind of weird to think about what this limit actually, tells us, right? I mean, yes, it gives us this, but think about what happens to this thing as n goes to infinity. As n goes to infinity, this thing, right, we have an n in the denominator here. That means the n is getting larger and larger and larger, which means this entire thing goes to 0. So now we have an a naught, but we can kind of forget about that. It's not really important here. We have a 1 plus 0, and so we have a 1, and then we have an n to the t, or n times t rather, and this n gets larger and larger and larger, and it goes to infinity. So we have 1 to the infinity. And what we're saying is 1 to the infinity is not 1 in this case. What? What? Right, that confused me. I had my Calc 2 teacher say that once. He was like, oh yeah, 1 to the infinity isn't 1. I was like, what are you talking about? That doesn't make sense. Multiply 1 an infinite number of times and you get 1. I mean, like, it was weird. But now you actually see it firsthand. You don't get 1, right? Because if you really think about it, we're deviating by just a little bit from 1. And so if you want to think about it that way, you can. So it's not really like 1 multiplied an infinite number of times. It's something really, really, really close to 1 being multiplied an infinite number of times. So it's not, I mean, like, you can think about it as 1 to the infinity. You can think about it as like kind of cheating. It's all up to you. But it's an interesting note. So now let's get into the stuff that matters though for you. And that's what equations you're going to be using here. Now we already found this continuous compound interest formula. That's what you're really going to be using here. If you're curious, this is the differential equation where it comes from. All right, or well, we actually found this equation another way, but if you think about the differential equation from this, it would be this guy right here. So let's do an example here. This will be quick, I promise, and then you're home free for this video. But I've invested $1 million into that new tech stock, right? I said that this tech stock is going to give me 6% interest, and now we want to find the following. We want to find how much money will I have after 2 years. Okay, that's going to be part A. And we also want to find how long it would take me to double my money. Okay, so first off, how much money would I have after 2 years? Well, let's pull up that interest equation. A equals A naught e to the RT. And if you want to write this as A of t, you can, you don't have to. Okay? Well, after 2 years, right, that's A of 2, right? We're plugging in a 2 for t here, right? So we know that we're going to be plugging in a 2 right here, okay? But we can also plug in for A naught and R, right? A naught, we know, is $1 million. So just to cheat, I can write that as 1M. And our rate, our interest, right? Just all you have to do, we're not going to add 1 to this. All we have to do is just convert 6% to a decimal. And when we do that, we get e to the 0.06 times 2. That's all we have to do for this. And when you put that in your calculator, you get $1,127,496.85. Okay, this is the amount of money that I will have made after 2 years. Okay, and so that right there is the answer to A. Now for part B, how long would it take me to double my money? Well, that's asking, right? And this is actually something that we've talked about with the half-life equation. We would not need to know how much I've initially invested to answer this question. We wouldn't, because we know the rate of interest, and we know that if I've doubled my money, that means that my A is going to be twice the initial amount, right? And so just be on the lookout for that. They might not give you your initial amount that you've invested and ask you how long it would have taken you to double your money. If they have, now you'll know how to solve it. Because really, this is just going to be 2 times A naught. That's going to be your new A. You get that's equal to A naught times e to the, we know R is 0.06, and we have t. That's what we're trying to find here. Now again, you could have plugged in what you know A naught is, but you don't need that. We can divide that out on both sides. And when we do that, we get that 2 is equal to e to the 0.06t. And solve this equation, we can take a natural log on both sides. And we get natural log of 2 is equal to 0.06 times t. Divide by 0.06 on both sides to solve for t. We get that t is equal to natural log of 2 over 0.06. And that right there is 11.55 years. Okay, hopefully I feel like I was writing way too fast there, so hopefully I wasn't going too fast for you there. But that is the time it would take us to double our money. So that right there is going to do it for this video. I hope this was able to help you, and I know we were only able to do 4 problems in this video, but I did have a lot of conceptual stuff that I really wanted to go over, because that is important with exponential growth and decay, right? To know all that stuff so you get where these equations are even coming from in the first place. Anyways, we were only able to go through 4 problems in this video, so if you want plenty more, go check out my full Calc 1 course, which I have linked in the description down below. But that's going to do it for me for this video, so I'll see you soon.